Welcome to Yung Tuition. I am Yung. Let's continue discussing basic issues in physics and their implications in other fields. In my previous talk, I argued that the Planck radiation law is incomplete because it is only described the frequency distribution of energy density of thermal radiation in vacuum. Yet, it doesn't tell us how thermal radiation is generated in the first place in matter. So just one knows the Planck law doesn't necessarily mean one can formulate thermal radiation from any given object, such as gas. Today, I'm going to discuss how Planck figured out his empirical formula in agreement with the experimental observations. More importantly, an early formula by someone else for thermal radiation enabled Planck to do so. So, are you ready? Let's go and have fun. Since the Planck law for blackbody radiation is exclusively focused on thermal radiation or thermal radiation field, the basic question is, what is radiation? As electromagnetic waves were demonstrated by Hertz in 1880, it could be argued that physicists must have known the observed thermal radiation can be related to electromagnetic waves, including Wien and Planck. However, none of them had explicitly dealt with the origin of such electromagnetic waves in their theoretical approaches. Instead, they were merely puzzled by the observed frequency-dependent energy density of thermal radiation itself in relation to Boltzmann distribution. As pointed out by one viewer, Planck went even further to exploring the radiation energy in relation to entropy in thermodynamics. Based on classical physics, Rayleigh and Jeans had derived the law for radiation by assuming radiation energy in a cavity can be theoretically formulated if the number of possible modes of oscillation and the mean energy per mode can be derived. To do so, one has to use the weird idea in physics called energy density of the field. By definition, energy density is energy per unit volume. It can be written as this form, where n is number of the standing wave modes in the given space, and E bar is the mean energy per mode in Joule. Consider a cubic cavity surrounded by heated condensed matter. The number of modes seems infinity, but if we are interested in a particular wavelength or frequency, then we have this simple relation in one-dimensional case. L equal to n multiply half wavelength, which can be rewritten as n equal to 2L divided by c, the light speed, and multiply the frequency nu. Using a sphere with its radius equal to n, which is normally considered as phase space, the number of modes can be written as 1/8 of the volume of this 3D sphere because the number n is always positive. N over V equal to 80 pi multiply nu squared divided by cubic of the light speed, c. Now, how about the mean energy per mode? In thermodynamics, as you know, the equal partition theorem states each degree of freedom of particle has the same amount of energy at equilibrium state, kT, where K is a Boltzmann constant. Of course, this is classical physics. So the energy density for radiation can be written as U equal to 8 pi nu squared divided by c cubic multiply kT. In doing so, however, the charged harmonic oscillator became completely irrelevant to phasor formulation of thermal radiation, such as the mass and the charge of the oscillators. Remember this. This formula for radiation is known as Rayleigh-Jeans formula, which is consistent with experimental observation only in the low frequency region, but gives a divergent prediction for energy density at high frequencies, called the ultraviolet catastrophe in many a textbook. In 1893, Wien first proposed an ad hoc formula to eliminate such an catastrophe, which is known as Wien radiation law, where W is a constant. Notice that this is what I rewritten based on its original form as this, where the A and B are two free parameters. I put them here side by side for your convenience. By highlighting the product W and nu, it is clear that it represents energy because KT is also energy as used in deriving the Rayleigh-Jeans law above. So it is Wien who first arrived at the important formula for the element of radiation or radiation field, known as Planck quanta, used by many people, or photon energy. Why didn't Wien go further to interpret his empirical formula? Anyone know? Interestingly enough, Wien borrowed the Boltzmann distribution to successfully get rid of the unwanted ultraviolet catastrophe, at least phenomenologically. Despite that, Boltzmann distribution is for classical particles such as atoms and molecules, rather than electromagnetic waves or photons. As I discussed before, the Planck law in terms of energy density of radiation can be written as the following, where h nu is the Planck's quanta, k the Boltzmann constant, and T the equilibrium temperature with matter. In my opinion, the formula proposed by Planck in 1900 might have been derived from two limits of the radiation frequency in line with, should I say, in light of Wien's law for radiation, not by himself independently. But how? Simple. First, when frequency is very high, the index can be very large than 1. By omitting the negative 1 in the denominator, we have this formula, which becomes the same as Wien's law for radiation, although Wien didn't use h. And of course, Planck knew Wien's law is consistent with experimental observation in high-frequency regions. On the other hand, Planck also knew that Wien's law at a lower frequency range cannot perfectly explain the latest observation by Robbins, the experimental physicist who also first observed the infrared absorption spectra of carbon dioxide and water vapor. Given the fact that classical Rayleigh-Jeans law works for very low frequency, it could be argued that Planck's key contribution was to mathematically figure out a function that can give Wien's law and the Rayleigh-Jeans law at high and low frequency, respectively. Here is what Planck might have done around the Christmas in 1900. First, he rewrote Wien's law as this, so that the E exponential becomes the denominator. Once he knew the latest experimental result by Robbins, Planck knew Wien's law underestimated the observation in low frequency region. He might simply make the denominator smaller by subtracting a positive number p. Then, using the first two terms of Taylor's series for the exponential function, Ex is approximately equal to 1 plus x if x is much smaller than 1. So, by choosing p equal to 1, he could easily obtain the Rayleigh-Jeans law in low frequency region. Voila, done. So, it could be argued that Wien is a real father and Planck is a son for the discovering of the energy formula for the quanta or photon in modern physics. Nowadays, unfortunately, only Wien's displacement law is taught in many physics textbooks, as if it were derivative from the Planck's law for the radiation, which seems unfair. If we plot the two laws at the same equilibrium temperature, you can see Wien's law is exactly the same as the Planck's law in high-frequency regions. It should be pointed out that, however, neither Wien nor Planck and other physicists then could realize the idea that the thermal radiation or electromagnetic field should be described by massless particles called photons, as invoked in quantum field theory many years later. It could also be argued that neither Wien nor Planck foresaw what their laws for radiation implies in relation to a totally new statistical mechanics in physics called quantum statistics, which was to be first discovered by a young man in India. I'm going to discuss next time.
50 years ago, when we were young, we had one great idea.
Thank you for your watching. Thank you for making comments, and thank you for your donation. See you next time.